welcome back to everybody. Let's talk about the old comparison tests. So we were at the very end last time we were talking about the limit comparison test, and I asked you to do one which is not really possible to do with the limit comparison test. I don't know if this was a typo or just a mistake, but to refresh our memory, let's just try the sum of n plus 2 to the n over 5 to the n. I had asked you to do, the one I asked you was that, but it had an extra thing in the denominator which messes the whole thing up. So that one, I don't think we need to go through all the details about how you would have done that other one. The one that I asked you at the end last time is not straight up impossible. It's just that one would require doing one step of the ordinary comparison with the inequality and then another step of the limit comparison, which is a little convoluted, and I didn't really intend for you to have to do it that way. Can you see the screen okay? Is there glare? It's all right? Okay. Maybe from where I am, it's hard to see, but I can see that one just fine. Anyway, let's try to do this, and our job is just to test the convergence using, well, anything but, I mean, what we were talking about that last time was the limit comparison test. All right, remember the idea is you look at that thing, and on the top and the bottom you look for what is the dominating term, and then you compare. So in this case, the dominant terms on the top, I see 2 to the n versus n, but in general 2 to the n is much bigger than n, and so the dominant term on top, I'm going to choose 2 to the n, and on the bottom 5 to the n. This is what most people were trying to do on that one from last time. It's just because of the extra nonsense on the one from last time, this ends up not working. But it should work fine for this particular example. All right? And then I hope everybody remembers how to do the limit comparison. So we look at lim n goes to infinity of the ratio, this thing, n plus 2 to the n over 5 to the n, divided by 2 to the n over 5 to the n. And then what you're looking for is if this limit exists and is not zero, is positive, then the convergence of the two series are the same. So this limit, as I would simplify this, you have to deal with these big fractions, but this is n plus 2 to the n over 5 to the n, writing it as a multiplication by the reciprocal, like so, right? And then we can cancel the 5 to the n's, and what remains is just n plus 2 to the n over 2 to the n. And then how do you deal with this? I would say use the L'Hopital's rule. Because I have this, if you just look at this limit directly, I see infinity over infinity. And so doing the L'Hopital's rule, I get 1 plus 2 to the n ln 2. That's the derivative of the top and the bottom. The derivative of the bottom is 2 to the n ln 2. Again, this still looks like infinity over infinity, so I do the L'Hopital rule again, and then this will really be the end of it. L'Hopital rule, again, the 1 on top goes away, and what remains is 2 to the n times ln 2 times ln 2. There used to be a ln 2 there, but I get another one because I'm taking the derivative again of 2 to the n. And on the bottom, sorry, this is messy, 2 to the n ln 2. And on the bottom, 2 to the n times ln 2 times ln 2 again. And this limit is 1. All right? Yes?
Instead of doing L'Hopital's, can you just say 2 to the n over 2 to the n is 1?
What about the n part then?
When it's like to a factor, don't you just look at the biggest?
I wouldn't say that. So there is a rule about if there's a polynomial on the top and the bottom, you look at the degrees, and if the degrees are the same, you take the coefficients. These are not polynomials though. Like this I mean, what you're saying does give the right answer in this example, but I don't really feel comfortable just saying that as my immediate conclusion. All right. Anyway, all of this ratio business is a 1, and the fact that that is, so this is greater than 0, so that means the convergence of what I'm looking at, n plus 2 to the n over 5 to the n, and the other one, which was just 2 to the n over 5 to the n, are the same. And now I look at this one, the convergence of that, sorry, this is 2 to the power n. Does that converge or not? And can anybody say why? Yeah?
It converges because the r value is less than 1.
Yeah, right. This one is geometric. I would think of it, sorry, as 2/5 to the n, right? And so this converges because this is geometric with r equals 2/5, which is less than 1. All right? So since that one converges, it means the one that we started with also converges, which is what we were trying to get at. So this converges. The end. All right? These ones are a little long-winded, even if you know what you're doing, but that's how we do it. Sorry for asking you one that was not really possible last time, without extra tricks, at least. All right. There you go. This is a fairly straightforward example of using the limit comparison test. All right. Great. Let's get on to something different. I want to go on to the next section here. So what we just did was the comparison tests, including the ordinary comparison test with the inequalities, and then this limit comparison test, which to me is a little easier to work with, although sometimes the other one is necessary. The next section is all about alternating series. Alternating series. So this is just another sort of trick that you can sometimes use to show that something either converges or diverges. And actually what we're going to talk about in this section is about, it's a test for convergence. Actually, you can't use this test to show that something diverges, but you can use this test to show that something converges. So alternating series, first of all, what an alternating series means is just that, so alternating series, it means, I think what you think it means. Alternating in terms of the signs, it means as you add these things up, the signs go back and forth, positive, negative each time. So alternating signs means the signs of the terms alternate, positive then negative, etc. So for example, the classic, the simplest one of these would be that. This is, minus 1 plus 1, minus 1 plus 1, minus 1 plus 1. And we have discussed this. Does that converge or diverge? This, fill in the blank. Verges. Con or die? Anyone remember if you go minus 1 plus 1, minus 1 plus 1, does that actually add up to something or does it diverge? It diverges. Yeah, this is one of those sort of playground stoner conversations. Playground or stoner, not both. I didn't have a lot of stoners on the playground when I was a kid. Diverges, right. If you think this actually adds up to something, I would ask, what do you think it adds up to? You can make a good argument that maybe this should add up to 0 because they all cancel, but you can also argue that they should add up to minus 1 if you save the first one, which is negative 1, and then cancel all the other ones. Those other ones all cancel, and you just get minus 1. Anyway, this one diverges. The partial sums don't actually have a limit. They don't converge to anything. Or something like, how about this? Minus 1 to the n over n. We actually haven't discussed this one, but this would be negative 1 plus a half minus a third plus a fourth minus a fifth plus blah, 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 etc. All right? This one I would say is not really clear to me if it converges or diverges. Not obvious. Actually, this is the simplest example, which falls under the category of what I want to talk about today. So this one converges, I will say. Actually, this one does converge, I happen to know. But the way to demonstrate that that one converges is by using what we're about to talk about, which the book calls the alternating series test. So this is only used for alternating series, but it's a way to tell if a alternating series converges or not. All right? So anyway, let me just say in general, we'll come back to that specific example, but generally, an alternating series looks like sort of, I will say it like this: B1 minus B2 plus B3 minus B4. Usually we write them with A's, but we write them with A's when it's always plus. And our book uses B's for this alternating series because, technically speaking, like in this example, the second term here is not B2, it's negative B2. But if you want to talk about these things individually without the signs, they call those the B's. But anyway, the individual terms alternate. So if I were to graph, sort of make a little plot of the sequence, that is not adding them all up, but just where are those individual terms. The sequence is like something like I'm going to draw points where they flip back and forth between being positive and negative, right? And if they are going back and forth between positive and negative, I mean, maybe they converge and maybe they don't. But it's always the case that as you sort of go from one to the next, they go above the line or below the line. So the first thing that we can say is they don't always converge. A sequence like this, which goes alternating, does not always converge, like minus 1 to the n doesn't converge. So there's no guarantee that it will converge. But what if they also go to 0? So what I'm referring to is a sequence in which it alternates the signs, but the points gradually get closer and closer to 0 like that. All right? Those points, so here the sequence itself converges to 0, but what about the series? That's what I want to talk about. And it turns out any such series where the individual terms go to 0, this is a guarantee that the series itself converges. All right, so I'm going to write this as a theorem, and then we'll do some examples. It's fairly, well, we'll see how easy it is to work with. So this is called the alternating series test. The alternating series test. And it says, in this alternating series, if I have something that looks like minus 1 to the n times b to the n, which if I were to, and actually, they like to, I'm going to change this to minus 1 to the n minus 1. That's just so that it starts with b1 being positive, minus b2 plus b3 minus b4, etc. All right. In this series, if the bn's are decreasing, that is to say bn plus 1 is always less than bn, and the lim of the bn equals 0, then the series converges. The sum minus 1 to the n minus 1 bn converges. All right, this is called the alternating series test. So if you are presented with an alternating series, and these two things have to be true. The bn's are decreasing and the limit of the bn's equals 0. Then the series automatically converges. This is the theorem. So when it comes to using the alternating series test, generally I would show you an alternating series and then say, use the alternating series test to show that this converges. What it amounts to showing are these two things. The b's are decreasing and the limit of the b's equals 0. If you can show those two things, it means that the series converges. All right? Again, it doesn't tell you what the series converges to. It's just that it converges. And I will point out, this is only about converges. So it says if these two things are true, then it converges. If one of those things is not true, then you just don't know anything. So it does not mean, if you check each of these and one of them isn't true, that does not mean that the series diverges necessarily. It just means I don't know whether it converges or not. So this alternating series test can only be used to conclude that it converges. Maybe we're going to do a bunch of examples of this, but I would like to try and give us some explanation about why you should believe this is true. I don't want to do a real proof here, but why it's true. Consider if I were adding up these things, b1 minus b2 plus b3 minus b4 plus b5 minus etc., right? I want to know as you go here, adding and subtracting, does it actually like converge to a specific value, or does it maybe go off to infinity or minus infinity or oscillate or something like that? Check it out. I'm going to try to draw a little picture here of the partial sums. So the first partial sum is just b1. The second would be b1 minus b2. The third one would be b1 minus b2 plus b3. These, remember, are the partial sums. And I would like to somehow see that these partial sums actually are getting closer and closer to a particular value. That's what it means for the series to converge. And check it out. I'm going to try and draw a picture here. This is a picture of the real line. Maybe here's 0, right? And where is S1? S1 would be over here, and actually S1 is equal to B1. And B1 is positive. Let's just say B1 is positive. That's why I put a plus on the first term like that. All right? So S1 would be over here. Actually, can I make it bigger? S1, let's say, is like way out there, all right? Where this distance across here is B1, all right? Where is S2 on the picture? That's what I want to know. S2 looks like B1 minus B2, so it goes back this way to the tune of B2, like a distance of B2 that way measured from here. And we have assumed that the BNs are decreasing. Can you see that? That means B2 is going to be less than B1. So when I look at the next partial sum, S2, it goes back this way by subtracting B2, but B2 is smaller than B1, which means when I go back this way, it actually goes sort of maybe that far, I don't know. It doesn't leave this little interval though, right? It doesn't go past 0 because the B2, so this little distance here is B2. It goes over by B1, which was positive, and then it goes back by B2, but B2 we have assumed is less than B1, so it doesn't go way out here. It goes back this far, all right? And then when I add on the next one, B3, it's going to go back to the right, but again, since B3 is less than B2, it doesn't go way out here. When I add on B3, it goes maybe only that far, right? And that's where S3 is. Can you see what's going to happen if I continue this? What happens is each time it'll kind of go back and forth. Maybe there's S4, and then maybe here's S5, and here's S6 maybe. Each time you add on a new piece, it's going to go back in the opposite direction by a little bit, but each little bit will be littler than the bit before. And is it believable based on this picture? This will actually eventually converge to a particular value because it's a bunch of back and forths where the back and forths, the width of these things is shrinking every time. And so that means this will eventually just kind of continue narrowing in forever and eventually lead to a value where it converges. All right. So this is not a real proof, of course, but this is the basic idea behind why the alternating series test is valid. It's because if these things are decreasing and eventually becoming zero, then this will continue bouncing back and forth in narrower and narrower little intervals, and eventually it'll converge to a particular value. All right. Anyway, let's try some examples with these guys. So here's the short version for an alternating series. You can prove it converges by showing, you have to show two different things. The first is that bn plus 1 is less than bn. That's the first thing. And the second thing would be lim n goes to infinity, bn equals 0. All right? Provided you can do those two things, then you will have shown that the series, the alternating series, converges. So let's try actually that first example that we had at the very beginning there. How about minus 1 to the n times 1 over n? And I'm going to just so that I begin with a positive, I'm going to make it n minus 1 here. All right? This actually, if you were to write out the terms, it looks like 1 minus a half plus a third minus a fourth plus blah, blah, blah. All right? This is an alternating series, and this has a name actually. This is called the alternating harmonic series. Just 1 over n, like all positive, that's called the harmonic series. This is the same thing, but it alternates the signs. So this is called the alternating harmonic series. All right? We have to show those two things about the b's. So I didn't say it, but let's show that it converges. All right? What are the b's? The formula for the b's in this example, the b's, remember, is basically the things you see in here, but without the signs. All right? The minus and the plus are not part of the sequence of b's. The b's is everything else. So in this example, bn is just 1 over n. So the b's don't include the signs. When you're doing these examples, the sequence of b's are just the numbers in there, not including the signs. All right? So in this case, bn is 1 over n. So we need to check each of these two things. So the first is that it's decreasing, so let's check that first. And you have to write, some kind of words to justify each of these things. And I hope everybody remembers how to show that a sequence is increasing or decreasing. In this case, we want decreasing. I will say I want to show that, bn plus 1 is less than bn. This is the same as 1 over n plus 1 less than 1 over n. That's how you would begin. You plug into the sequence is 1 over n, and so I want bn plus 1 would be 1 over n plus 1. Bn would be 1 over n. And then, is that really true? I mean, you would want to prove this somehow. I would say here, you might just look at it and say, yeah, that's true, because the denominator on the left is bigger than the denominator on the right. Or if you prefer, you could say something like multiply across here. This is the same as n less than n plus 1. Anybody think that's true? Yes, that's true. All right? If you don't believe me, I'm going to go way too far here. You could subtract n from both sides, i.e. 0 less than 1, which is true. All right? So it is decreasing. That was the first of the two things we have to show, right? First of all, that it's decreasing, and then second of all, that the limit of the bn's equals 0, okay? Both are easy in this example. And now the limit is the second part that we have to show. So I want to show, that's what WTS means. In this step, I want to show that lim n goes to infinity, 1 over n equals 0. And is that true? Yes, that's true. I mean, that everybody knows that, right? Which is true. So in a more typical example would be more complicated, and you'd have to actually go through some arguments for each of the two parts. But this is the easiest possible of these examples. All right, so anyway, you should write some words of conclusion here. So the BNs are decreasing with limit 0. So the original series -1 and -1 times 1 over n converges. Right? This is what the alternating series test says. If the terms are decreasing and their limit is 0, then the alternating series converges. All right. Great. Let's do, I got one more example, and then I have some for you guys to try. There are really two steps. There's that decreasing part and then that limit part. Let's try, how about show that this converges? How about 1 minus a half plus a fourth minus a eighth plus a 16th minus, etc. All right. These are powers of 2 in the bottom. So we should, that is, obviously, it is an alternating series because the signs are alternating. We should write down a formula for Bn. Can anybody give me a formula for Bn in general? Something about something. Yeah?
-1 to the n over, or times 1 half to the n.
I want to say something like 1 over 2 to the n. So remember the sequence of b's does not include the sign, so you shouldn't try to put the -1 to the n in there. If I were writing this as a series, the sum of an, then that would include the sign, but the b's that we're talking about do not include the sign. This, I think, needs to be modified slightly because we're starting n equals 1. I want to get 1 over 2 to the 0 to begin with, so I think it's that, right? But that's a little technicality. But those are the b's, right? The b's never include the sign information, but you sometimes will have to kind of look at the series and figure out what the formula for the b's are. All right, let's try and do each of the two parts. The first would be to show this is decreasing, and the next would be to show that the limit is 0. I think, again, in this example, those are both pretty easy. But anyways, this is decreasing is the first part. So first I would just write what I want to show. Want to show that Bn plus 1 less than Bn, right? That's what it means to be decreasing. And then plug this into the formula up there, i.e., this is the same as 1 over 2 to the n minus 1 plus 1, so that's just 1 over 2 to the n less than Bn, 1 over 2 to the n minus 1. Right? I am plugging in n plus 1 to the formula for the sequence Bn. And then is this really true? I would multiply the denominators across like we always do. This is the same as 2 to the n minus 1 less than 2 to the n. And I think that really is true, right? I have a lesser power on the left and a greater power on the right. So this is true. I will remind you again, when you are writing these steps down, you must put some words in there, or at least like WTS and IEs or whatever. If you only write this, it is not clear what you are talking about. You're just simplifying a bunch of stuff. All right. It needs to be clear that the flow, like the logical flow of the argument, is actually kind of backwards here, which is the way I intend. But we start by writing what we are eventually trying to conclude, and then we simplify that until it looks obvious. Okay, anyway, that's the decreasing part. And now the limit part. Here we want to show that lim n goes to infinity of bn equals 0. And this is, in this example, this is it, easy. Lim n goes to infinity. Bn is 1 over 2 to the n minus 1. That really is 0 because this looks like 1 over infinity, basically, right? Maybe I'll put shoon to indicate that we're done. Having shown those two parts, it means that the alternating series converges. So the alternating series converges. Then I can write my converges. I'll put the shoon down there. All right. Proper shoon placement. This is how it's done. I got 2 for you to try. I made sure to check very carefully that these are actually doable using the methods under discussion. All right? So, show that this one converges. And I got a second one here. You will see ones like this on the homework for this section. Show the first one converges, show the second one diverges. Now, the somewhat tricky thing about this is, remember I said, I tried to make it clear, what we talked about today, the alternating series test, can only show you that something converges. So, in this case, this is an alternating series. To show it diverges, you don't do it like we just did. You must use some other method. So, if you want to show that something diverges, you don't use the alternating series test. You just have to use one of our other methods. So here you could use the comparison test, the integral test, any of these guys. What else have we talked about? The limit comparison test, of course. And then there was one, oh, that red cross. They're on me again. One of these days I will give them a piece of my mind. There's one other very simple test which sometimes used, which is just that if the lim of the an is not 0, then it diverges. This is something we talked about. This is one of the first tests that we talked about, is that in order for a series to converge, the terms on the inside, their limit has to be 0. And if that's not true, then it automatically diverges. But anyway, I will leave it to you to decide which of these methods you can apply successfully here. The first one, though, goes very much like the one we were just doing. So see what you think. Oh, I think there's a typo. I don't know if this matters. Sorry. I meant 3n squared plus 1 here. I think this, I don't think it really matters, but it makes the inequalities easier to handle, I think. If you worked it out the other way, that's fine too. I meant for it to be a plus 1. Okay. Okay here. Just because of that. Yeah. Yeah, they're not entirely. It's just that's. Am I right here? Yes.
Because the degree is higher, but is that not, so should I keep going with it?
I had a better reason why.
Oh, okay, gotcha.
Okay. So now this is like. You have these fractions, and you're gonna do the line across. Alright. Okay. How did you, that's a plus one, right?
Yeah.
Alright. That's a good. That's good here. So yeah, you something else. It's 2 times n. She changes. I started with minus. Yeah, that shouldn't really matter. Yeah. Okay here. Second one. Yeah, I would say, so the second one you can show that it diverges by using the complement. You can see that, it's hard to see. This thing about the limit. Did you see that? So here you could show that the limit of this isn't equal to 0. That means you just take the limit of that as n goes to infinity. This is like almost. So that is just a free
I did it, but I don't know.
I was just wondering, what over is
Were you linked about it?
like two
What
over?
like other series did you choose?
I did 3n over 2n,
But this is not the work.
Okay.
I thought you.
but I wasn't sure if you could do that because you're kind of just ignoring.
I try to make it a limit. Yeah.
Yeah.
You can only do that. You can only make it a limit.
I think you
part.
I mean,
No, I mean,
I
it's
did
your
it as if you could and it got me an answer, but.
Yeah, because you just boil out and then it's like
You have to show that it's increasing. also that.
No, I still.
Well, no, actually, it looks like to me what you're showing here is that the limit is.
Yeah, well, that's what I was trying to do.
Yeah, that's the second part. Yeah, that's
Yeah.
right, that's what you said.
Yeah.
Okay, and then for the, you also need to show that this sequence here is decreasing.
Okay.
I'm gonna come around again and then we can talk about how's it going.
Which of your strategies are you using?
I would suggest the last one that I wrote.
Okay.
Yeah. The comparison and the integral, so the integral test doesn't work great because this, the integral test, remember, means you change all of this into the integral of that function, but -1 to the power x is a bogus, that's not a continuous real function. So don't do the integral test. Comparison test also only works when the sequence is all positive. So we can't do that either. So do the last one. The last one is actually very easy. It's
Thanks, Gabe. I had a question though, so you do the limit test, you said if it doesn't equal, if A of n doesn't equal 0, then it diverges, but then weren't we doing up here when it equals,
I think you just take one
when it equals 1
1 over 2.
This is
Do 3n minus 1.
the over 2 limit.
Yeah, it'd be the same degree, right? So you need 0 over 2.
Is not 0.
One would be 0 over 2.
Oh, yeah.
Yeah.
If that ratio is not 0, then the two sequences have the same.
doesn't mean that they converge.
That's right. And
Okay,
also,
so that's
what
what I
you're doing here is, this is really like an, that's an, and you're dividing by another an. So
Uh-huh.
you're not actually showing the limit to an, it's the limit of that fraction.
Okay, got it.
Still doing okay over here? All right, let's try and work these out. I see some good, some people were very puzzled about the second one there. The second one is kind of out of nowhere because this is, to do the second one is not related to what we've been talking about today. It's just I wanted to show that you cannot use the same test to show that it diverges as the converges. But the first one should go fairly nicely. Let's just make sure. And I saw people seem to be doing okay with this one. Some people just decided to do the second one first, thinking that it would be easier. It is not. Anyway, so I have to show, first of all, decreasing. Well, maybe I'll write, first of all, the sequence of b's is 2n over 3n squared plus 1. A few people magically turned it into 2 to the power n, which it's not. So first of all, decreasing. All right, what I want to show is that bn plus 1 is less than bn. And this, writing this out, gives you a big bunch of inequalities. But this will say 2n plus 1 over 3n plus 1 squared plus 1 less than 2n over 3n squared plus 1. And then you need to do a bunch of simplifying here involving do the FOIL down there and then simplify, simplify, simplify. Do you mind if I cut out the details? Eventually I got this down. I was simplifying everything, got it down to say something like 1 less than 3n squared plus n. This is the most simple that I could make that. Maybe you got some slight variation on that. But anyway, I would say this is definitely true because I have these guys over here, n is greater than 1, and so this 3n squared plus n is greater than 1. So this is true since n is greater than 1. All right? I hope that everybody is okay doing these. You know, I was a little dismayed to see on the homework and on the quiz I asked you to show that something or other is decreasing. It is not good enough to just like plug into your calculator a few values and say, see, it goes down every time. That's not good enough because all you would have demonstrated is, see, it goes down, you know, this 1 or 2 times that I showed you. But you have to demonstrate in general that this always is satisfied. Yeah.
Just going through the steps real quick.
Yeah, we can do the steps here. Yeah, thanks for asking. I shouldn't be so cavalier about skipping. So what I would do here is distribute on top first, 2n plus 2. On the bottom, do the FOIL there. It's 3n squared plus 2n plus 1 plus 1. Less than, here is the same as it was. And then distribute the 3 on the left side. Sorry. 2n plus 2 over, distribute the 3. 3n squared plus 6n plus 3, and then plus 1. Let's see if I can actually make it to where I said I got. All right, doing okay so far? Now I'm going to multiply across the denominators. So the left side will say 2n plus 2 times 3n squared plus 1. That's the denominator that used to be on the right. And then the other on the other side, 2n times the denominator on the left. 3n squared plus 6n plus 4. I added 3 plus 1 is 4. All right. Finally, do the FOILs and distribute on the right side. So on the left, it'll say 6n squared plus 6n cubed. Sorry, I should have started with 6n cubed plus 6n squared plus 2n plus 2. That's the FOIL on the left. Am I doing all right? And then less than, distribute on the right. 6n cubed plus 12n plus 8n. Yeah?
12n squared.
12n squared. Yes, thank you. Anything else? Now? All right. And then we can maybe put everything on one side that's convenient. So we can straight up cancel the n cubes. I have 6n squared on the left, 12n squared on the right. So I'm going to push them over to the right. So it'll be 6n squared on the right, 2n on the left, 8n on the right. Subtract it over to the right. It'll say 6n is like that, I think. And then if you just divide through by 2, just to simplify a little, this is what I said before. I think that's what I said before. And now that is definitely true because n is bigger than 1. Great. Right. There's a lot of steps in there, but I hope it came together for you. Okay, that was only half of it, right? That's the showing that the sequence is decreasing. Then I also have to show the sequence has limit equals 0. So that would say lim n goes to infinity. Bn is 2n divided by 3n squared plus 1, right? Is this limit equal to 0? How did you argue that? I actually would say just straight up, it is 0. Why is it 0? Yeah.
The denominator is larger than the numerator.
Yeah, right. The power on the bottom is bigger than the power on the top. These are polynomials, and the degree on the bottom is 2. The degree on the top is only 1, so this limit equals 0. This is because degree on the bottom is bigger. All right. So those two parts together means the series converges. Right. Okay, can we talk about the other one? So the other one was a bit of a out of nowhere, but just to demonstrate, remember that when you're trying to show something diverges, you cannot use the alternating series test. You have to just use some of our other tests. And actually, in this particular example, none of the integral test and the comparison test both are not appropriate for this example. And the reason is because if I try the integral test, it would turn into integral 1 to infinity minus 1 to the x, 3x minus 1 over 2x plus 1 dx. And that right there is bogus. I don't know if that looks bad to you, but minus 1 to the power x is not a real valued function. It's because, for example, this you can't do powers, weird powers of -1. You can do whole number powers of -1, but not other ones. Like, for instance, this is bogus because, for example, minus 1 to the power 0.5, this means the square root of minus 1, which is not a real number. So this is not a legitimate function of real numbers. So you cannot do this integral, at least not without knowing how to do complex number integration. So all of this is not going to work for the integral test. The other suggestion that I made is perhaps the comparison test. That also does not work. You can't use the comparison test, comp test, because if you recall, the comparison test requires that all the terms be positive. And so actually, any alternating series, you just can't use the comparison test on it because you need all the terms to be positive. So I would suggest the only other option which I mentioned there is this last thing. I don't know if you like the looks of this, but this is actually the easiest of the three that I suggested. This is just a fact that we talked about, maybe the first day we talked about series. If the limit of those terms inside isn't 0, then it diverges. And this limit is not 0. I think we can show. Lim n goes to infinity, minus 1 to the n, 2n over 3n minus 3n squared plus 1 is what that says, right? No, that was the other one. Sorry. It was 3n on top. Sorry. 3n minus 1 over 2n plus 1. Okay. This one. Is that 0 or not? I say it is not. I mean, when I look at this, I think this part here, when I take the limit, it converges to 3/2. That's because this is, again, a ratio of polynomials, and they have the same degree in this case. So this part here, this converges to 3/2, but this part alternates. That means this sequence, if you go down far enough, it ends up just looking like 3/2, negative 3/2, 3/2, negative 3/2, right? The number part of it converges to 3/2, but the sign is alternating here. That means this one here diverges because its absolute value is looking like 3/2, but the signs are alternating. So it does not converge to any particular value. So the lim of the ANs is not 0, so the series of the ANs diverges. All right. This one, I guess, is a little strange, but the moral of the story is for alternating series, when it comes to showing that they diverge, you just have to kind of use whatever tricks work. And it's for alternating series, it's usually this one right here, showing that this limit is not converging to 0. All right. This is the alternating series test. All right. Any thoughts about that? We still got a good 15 minutes or so, a little more than that. Let's talk about the next bit then. The next section is called absolute convergence. This is a special kind of more extreme type of convergence. You know, some series converge, some series diverge, some converge, and some absolutely converge, or they converge absolutely. This is called absolute convergence. So one thing that's interesting about, so of the examples that we've seen so far, remember, this sequence, or this series, is the harmonic series. It's just adding up 1 over n, and that one diverges. We've talked about that many times before. This is a p series with p equals 1. It diverges. But if you alternate the signs, this is something that we talked about today, this one converges. All right? They are the same numbers. The only difference is with the signs in front of them. All right. So the second one converges. The interesting thing about this is the second one converges, but if we make all terms positive, another way of saying that is if we take absolute values of each term, it diverges. All right. So the second series there, it does converge, but if you were to take the absolute values of all the terms, then it no longer converges. And so the terminology we use here is we say 1 minus a half plus a third minus a fourth, etc. We say that this converges, but it does not converge absolutely. Where what I mean by that is it does converge, but if you were to take the absolute values, then it would not converge. And that's what absolutely means. Absolutely meaning if I were to take the absolute values, then it doesn't converge anymore. All right? So here's a real, I will write a sort of technical definition here. If I'm talking about a series, we say this series of AN converges absolutely or another way of saying this is, or is absolutely convergent, if you want to say it that way. These are just two different ways of saying the same thing. Converges absolutely, or you could say it is absolutely convergent when the sum absolute value AN converges. Right? So just because the original series converges, it does not mean necessarily that it will be absolutely convergent. Absolutely convergent means if you additionally take the absolute value, then it still converges. All right? So a series converges absolutely when the absolute value of that series, when the series converges even after you take the absolute values. All right? And if that's not the case, so we do have some examples that we've seen where this is not the case. If the sum AN converges, but the sum absolute value AN diverges, there's a name for that. We say the sum AN is conditionally convergent. Conditionally convergent. Conditionally convergent means it does converge, but only if you keep the signs the way they are. And if you instead take the absolute values everywhere, it will not converge anymore. All right? The sum AN is called conditionally converges. This condition means sort of, the idea behind this terminology is it converges, but only on the condition that we keep the signs the way they are. This is my interpretation of why we use the word conditionally there. Only on the condition that we keep the signs how they are. If we instead make all the signs positive, then it will not converge anymore. All right? And the standard example when they ask you in the club, what is an example of a conditionally convergent? This is the standard example. This one is conditionally convergent. In the DMs, this one is conditionally convergent because it by itself does converge, but if you took the absolute values everywhere, it becomes the harmonic series which diverges. All right. All right, we got 10 minutes. I think we have time for one basic theorem, I guess. I'm going to write this like a formal theorem, and we can talk about the proof. It's not very complicated, though. This is about convergence versus absolute convergence. So some things which converge, they do not absolutely converge, but actually the other way around is always true. So it says if a series is absolutely convergent, then it is convergent. All right? This means absolute convergence is somehow like stronger. If you know something is absolutely convergent, automatically it is convergent by itself. Ordinary convergent. All right? If AN is absolutely convergent, then it is convergent. All right, let's talk about why this is true. So I'll write this like a proof. This is not going to be super formal, though. The thing that we're trying to demonstrate is if it's absolutely convergent, then it is convergent. So we're going to begin by assuming that the sum AN is absolutely convergent, absconv, i.e. what that means is the sum absolute value AN converges, right? And what we want to explain is to show that, then I want to show that the sum of AN without the absolute values also converges. If we know it converges with the absolute values, we want to demonstrate why it converges without the absolute values. And the trick is simply to add them together. Let's add them up. What happens when you add these two together? So I have the sum AN. Well, this is really what I want to look at. The sum of AN plus absolute value AN. All right. Can anybody say this is not a deep fact here? Each term here is either or. This is not a special fact about sequences. I'm just imagining any number you like, x plus absolute value x. What is the answer of that? Can you simplify that somehow? I think actually there are two possible answers. Yeah?
2x or 0.
2x or 0, he says. I agree. Why do you say that?
Because if x is negative, then it would cancel the absolute value, and if it's positive, it'd just be double.
Yeah, right. If x is positive, then I'm just talking about x plus x both times, which is 2x. If x is negative, then x is the opposite of absolute value x, and they will cancel and you get 0. So each term is either 0 or 2x, right? I mean, 2, I'm talking about 2 times it's actually 2 times absolute value AN. Zero or I think maybe without the absolute value. Nah, it's fine. It doesn't really matter. If AN is positive, it adds up to 2 times AN. Yeah, really you don't need the absolute value, but I'm going to keep it. It doesn't matter. And if AN is negative, you get 0. Okay, what that means is, so we can do some kind of comparison tests. Compare. What this means is when I'm adding these up, every one of these terms is either 0 or this. So each term is automatically, I can write comparisons like this. Right? And actually, I don't care about the 0 on the left side. Really, this right side is all that matters. And I should say less than or equal, because this is either equal to 2AN or this left side is 0. So it's definitely less than or equal. All right? But what that means is now that means by the comparison test, this has the same convergence. So I can say this. And on the left side, we can split the sum an plus sum absolute value an. And over here, I'm going to factor the 2 out. And anyway, we have assumed at the very beginning, I said assume that an is absolutely convergent. So that means these both converge, right? Because we have assumed that an is an absolutely convergent series. So these actually equal particular numbers, which means automatically this one also converges. It does not go up to infinity because it's less than this thing, which is converging. So this converges. All right. And this is what we wanted to show. If it absolutely converges, then the original thing also converges. All right. We got 5 minutes. That's enough time for one example concerning this business. So let's try. You can use this fact to show that certain things converge. Let's show that the sum sine of n over n squared converges. Now there are other ways that you can do this, but I wanted to consider this in terms of absolute business, right? Actually, I'm not so sure there are other ways. The standard way that I would think of doing this is by using the comparison test. Can anybody tell me, though, the comparison test does not apply here? Yeah?
It's not always positive.
Because it's not always positive. Yeah, I said a few moments ago, the comparison test, your sequence must be positive. I mean, the terms inside must be always positive, but these are not, because the sign of something is often negative, all right? The trick, though, is to show this converges, we'll show that it converges absolutely. And that automatically means that it converges, according to the theorem that we just talked about. If it converges absolutely, then it automatically converges by itself. We'll show that it converges absolutely, and then this will mean that it converges. All right. What's the point of that, though? So to show that it converges absolutely means we'll show that the sum absolute value sine n divided by absolute value n squared converges. Right? I took the absolute values of everything. Of course, on the bottom, absolute value n squared is just the same as n squared because it's a square. This is the same as absolute value sine n. But the absolute value on the top really does make a difference. All right. And how can we show that this converges? Well, now that I took the absolute value, these are all positive. So now we can use the comparison test. This is the trick. After taking the absolute value, they all become positive. These are all positive. So we can do the comparison test. All right? And what would I compare this with? Absolute value sine of n divided by n squared, I want to say is less than or maybe greater than something, something, something. Any ideas here?
Would you just multiply 2 in front of it?
2. You mean?
Yeah. Well, I'm just trying to show that like it doubles. Like with the last one, how you're doing that, you know what I mean? You want to do the same thing?
Yeah, I don't think. Yeah, this it's not really related to this business here. This was part of the proof of that thing, but here this is just a much more ordinary thing about, can I show that this is always less than something similar? What do you think? What do you say?
Absolute value of sine n over n.
Sine n over n. I wasn't going to say that. I think that's probably true, but I would say not helpful in this case. And I am thinking about, like, to me, what I don't like about this is the sine n. I would much rather it said something like 1 over n squared, because that's a p series, or maybe something with a power n, but that's not going to happen here. But any other ideas? What can I say over here? I would like to make it look more like one of our favorite series that we talked about. Yeah?
Can you just make the numerator 1? 'Cause
Yeah. I think we can just straight up say 1 over n squared, because here the numerator is sine of n, which is always less than 1, right? So this really is just straight up true, exactly as written. All right? So we can compare it in this way, which means, remember this is how the comparison test goes. The convergence, it's not exactly. So if the sum 1 over n squared converges, then also the sum of what we're looking for, absolute value sine n over n squared, converges. And does this converge? This part?
Yep.
It does converge because this is a p series with p equals 2. It's a p series with p equals 2. All right? And so, therefore, by the comparison test, my sum absolute value sine n over n squared converges. And so that means the sum sine n without the absolute values converges. Because if it converges absolutely, it automatically converges without the absolute. All right, that'll do. We'll try some more of those on the homework. Oh, I'm sorry.